What? What's going on? What's going on? Wait, what?
She calls herself like people other lucky cat.
Lucky Cat?
Yeah.
What's wrong with that online name? I think that's a cool online name.
Yeah.
My online name is Matt Grimes.
Wow.
Is it? I don't think so. No. I want to be called something like the Photon or the. Yes, Photon Master.
Change now.
Change it now, yeah. Yeah, I can see this working. Okay, quantum mechanics. Yeah. Now, Faisal, I'm telling you now, there might be some weird ideas in this. Do not interrupt me. If you have a question, wait for an appropriate moment to ask. Understand? Thank you. Correct. Don't worry, I still have you next week. Right, start. This is the last physics topic. Then you will be physics geniuses. No laughing. It's true. Right. Earth and Moon. And the formula for the force between them? Which formula is this? Provided by Mr. Newton. G m1 m2 over r squared. Okay, we did this. Now, look at this picture. Photon, electron. And the formula? K, Q1, Q2 over r squared. So, it'd be right to say that it's the same situation, correct? You have two bodies, a heavy one and a light one. The light one is in orbit of the heavy one. And the force between them is exactly the same formula, except just a different constant, and it is the charge rather than the mass. Not that that matters for the force. So, when this was discovered about 120 years ago, people thought, well, if the picture is the same and the force is the same, then the answer is the same. But it's not. What is happening here? Yeah, I'll explain why I'm saying I lied. If we go to this picture, it is possible for the moon to be at any level. It's different for each planet, but it could be anywhere, except of course on the planet, but it could be anywhere. And people thought, well, that's the same thing here, that the electron could be at any level. You could adjust it. After all, there is no such thing as a minimum distance. It can be at any distance. Recall that I said that. So this is why I now say that I lied. This turns out not to be the case. It turns out that the electron can only be at certain levels. This is what you learn in chemistry. The energy levels of electrons, the orbitals. It is impossible to put the electron between levels. It can't be done. It's like the electron can't sit there. It's because there's a minimum distance. The electron can be here or here, but not in between. There's only certain distances it can use. This seems very strange because on day-to-day life, I could be here, or I could be here, or if I want to, I could be in between the two. That's not what happens here. But I don't know. Did you talk about this in chemistry? No, but you've done energy levels and orbitals? But that's all. You didn't learn why, or did you know that it was impossible to be between orbitals? Well, it is. So that's what you learned. Okay.
No, but you said that the electrons can only exist in orbits.
Exactly. Which means that it's impossible for them to be in between the orbital levels. And now, another important experiment from 120 years ago. If you shine some light into a prism, you should get the full rainbow. Prism is a triangle glass. Now, imagine here we have a hot gas, something like the sun or whatever, a hot gas. And the light from the hot gas, we put it through a prism. And we get this picture here. And you notice something interesting, we don't get all the colours, we only get some of the colours. And there's some black pieces as well there.
What do you mean black body?
Oh, black body just means like a perfect light source.
Okay.
Yeah, don't worry about that. I could have just said perfect white light or something. So in the first one, we get the full colour. The second one with the gas, we only get some of the colours. So we need to think about why some of the colours might be missing. So remember what I said earlier, that what tells us the energy of the photon? The frequency.
But it has, most of the colors, like, I think it has all the colors for the edges.
No, there's colours missing.
Red, orange, yellow, green.
Yeah, but it doesn't have all the shades. That's what I mean by the colours are missing. So you only have some of the red and some of the blue shades. What was I saying? Oh yeah, so the colour tells us the energy level. So by having some colours missing, it means you're having some energy levels missing. So why might there be some energy levels missing? Why are some of the photons not coming out of the hot gas? Any ideas now? Why are some photons with certain energy missing?
Very sharp.
Yeah, why aren't they coming out? What's the cause of it?
They don't have enough energy?
Possibly.
Or the frequency are not visible to us?
No, that's the frequency should be visible. Well, let's have a look at the last one, and maybe this will help us to understand. So this situation is a bit different. Here you have a cold gas. We can't see a cold gas. It's not bright. It's cold. It's just like in this room, oxygen. We can't see oxygen because it's cold. If we made the oxygen very hot, we could see it, but we can't see it now. So what you do, you shine some light into the cold gas, and it comes out, and on the prism, we get all the colours, except some of them are missing. Now this one maybe is easier to understand. The photon enters here. The photon has energy. It loses energy to the gas. Some of the photons come out, some of them stay in. Why do some of them stay in? Well, it's because of the electrons. Remember earlier we said the electrons can be at certain levels. If the electron gets enough energy from a photon, it will move up to the next level. If it doesn't get enough energy from the photon, it will not move up, because it can only move up one level. It can't move up half a level. So if it gets enough energy, up it goes. What happens to this photon? It's gone, because it took the energy to move up the level. So the reason there are black parts here, this represents the electron energy levels that were taken so it could move up to the next level. These were rejected photons because they did not have the right energy. So that's what's happening in these pictures. The reason some of the colours are missing is because of the energy level requirements for the electrons to move up and down levels. So what's happening in the second one, if you think about it backwards, photon comes in, an electron moves up. What happens when an electron moves down? Photon comes out, right? Because there's different energy levels, it means the electrons can only move in certain levels, which means the photons can have only certain energy, which means they have only certain colors. So, photon comes out as the electron moves down. So, for example, photon comes in, electron moves up. But backwards, if electron moves down, then photon comes out. But you don't get all the photons.
So why is it only hot gas?
Because hot gas, by hot gas I just mean gas that we can see because it's giving off light. That's all I mean by hot gas. It doesn't have to be hot, it just has to be glowing so you can see it.
Without like air in this room, we can't see each other.
No, I'm not saying. When I say hot gas here, I just mean a gas that you heat it so it starts to glow. That's all. Can you see the air in this room? No, so we call this a cold gas. But if I took the air out of this room, put it into a box and heated it up, then it would start to glow.
But then we can see like the cold gas, it has a spectrum.
Yeah, the reason we can only see it is only because if I shine some light through the cold gas. If I didn't have this light, then this would just all be black.
Without black.
And without this one heated up, we wouldn't see it as well. Yeah. So are we clear why there's only certain colours here? Is it okay? Yes, that means yes. Indian, yes.
You said the photon go out.
Yeah.
Then what next?
Yeah, so remember we said the photon hits the electron and the electron is freed. You can do it backwards. If you stick the electron back, then out pops a photon, which is interesting. So, in chemistry you have different orbits. What's the first orbit? S1 or something? 1S, yeah, that's the first one. And then the next level up?
2s.
That's the next shell, is it?
Yeah.
Yeah. So when the electron is in the lowest orbit and a photon hits it, if it has enough energy, it will move up. But also, if the electron moves down, then a photon comes out.
So emit light.
It'll emit light. The electron can only be in certain orbits, which means it can only make certain jumps, which means only certain light can come off. Not any light, just the light for the energy jump it's making. So that's why you have this missing spot here. You'll need to write this down in a moment, but just before you do, what's really useful about this is every material has a different pattern. So this is like a fingerprint of the material. Each material has a different pattern. So you've done things spectrometers. What spectrometers did you do in chemistry? Just the mass spectrometer? And what does the mass spectrometer tell you? Mass to charge ratio, yeah. You can get spectrometers that, like for example, let's say I wanted to know what my phone was made of, for example. What I do is I take my phone, I put it into the spectrometer, it heats it up until it starts to glow, the light comes out, goes through a prism, this is captured by a computer, the computer looks at this, checks its database, and tries to match the result with what it knows exists. So it might say, this is 20% plastic carbon and 10% nickel or whatever like that. So, this is quite an important result. Every material has a unique spectrum picture. I don't know, you need to really heat it up and turn it into gas. So okay, I maybe won't do it with my phone, but I think what they do is they do it with like food, to check if it's been contaminated with something. So you might take some corn or whatever and heat it up, and then you look at it and go, yeah, this is the spectrum for corn. However, there seems to be some plastic or whatever contaminating it. Yes, you wouldn't really do it for my phone, but usually small samples, like food samples perhaps. Okay. Continuous means all the colours. Emission is for hot and absorption is for cold. If you can note this, please. Yes, please.
That's the reason why at night when you turn on the light, what you see is different from the
No, actually. The reason for that is because this light here, this light at the top, this is not white light.
not like the sun.
Not like the sun. Yeah. So, guys, that's a good question. Can you listen? This light here is not white light. It's not like the sun. If I put this light up the top in the prism, I do not get the rainbow. This light, I think, has more yellow and less of the other colours. And this is the reason why they say this light is bad for your health at night time. Because your body, the yellow part of the light is what tells your body it's daytime. So if this has more yellow in it, then it's telling your body it's really daytime, extra daytime. You know? So these are actually a little bit yellow. You can't really tell. They're a little bit yellow, orange. Or is it blue? I don't remember. It has one extra colour it shouldn't have.
Only works for the sunlight.
Yeah. Well,
Unless they can make a white one.
super technically no, because sunlight isn't pure white light. It's nearly pure white light. But if you look at the emission spectrum for sunlight, there are 2 shades of red missing. But I mean, it's the closest thing to pure white light that we have.
Why do we got these 2 shades?
They are because the light is coming from a helium-hydrogen gas. It's not pure white light. It's the spectrum for hydrogen and helium gas. I don't even know if it's possible to make pure white light, because if you think about it, the way to make light is by heating something up. So you'll always get a spectrum, because you're always heating something up. You know, can you make pure white light? I don't even know if you can.
But then, like, what lights do they use for the cool gas?
Oh yeah, this would all have to be a pure white light.
Which cannot be used.
It can practically be made. If you're using sunlight, it's the closest thing to it. Sunlight is only missing 2 colours, 2 shades of red. Okay, continue. Yes? Did you do this in chemistry? No, this is a new thing? Yep. But also, you don't have to heat it up. You can shine the light on the cold one as well. So I did see a phone app. The phone app uses the light on your phone. It shines the light on the material and it's reflected back. And it analyzes the light that it gets back to try and work out what the material is that it's looking at.
Really?
Yes. And the reason they're using this is because the idea is before you eat a meal, you put the phone over the meal and it can tell you what ingredients are in the meal and it can alert you to if there's something you're allergic to in the meal. I don't know. But I mean, there can't be that many of them. So type in some like spectrometer app. See if you can find it. Okay. Continuing. So we already talked about this. Okay, here's a quick question for you guys. Try and work this out. Are you all trying to look up the app now? Show me. Spectral Snap sounds like it.
Your spectrum. It shines the light from your flash and measures. So
Is it free?
yeah.
Try it out.
Yeah.
You want to read the description?
Yes, no, that's it. That's a version of it, yeah. Well, anyways, you can play with that toy later then. Okay. Can you try this question, please? So, the electron falls from state 4 to state 3. By the way, just to be clear, as we move up, do we get more or less energy?
Left.
More.
More.
This is most negative. Why is the bottom one most negative?
Because it has
Yeah, it's the most trapped.
Yeah.
As you move up, it's less negative, which means more energy.
Less energy is required to treat.
Exactly, yes. So, I just want to make sure you have the signs the right way around. Tell me how much energy is in the photon that's released when the electron falls from 4 to 3, level 4 to level 3. Yes, it is just a subtraction. That's all I want you to do.
Minus 0.65.
No, positive.
Positive.
Yeah. And roughly that, isn't it? Or 66, is it? 0.66.
Yeah.
Yeah. Okay. Next. Same idea, except this time, tell me the frequency of the photon.
This is an electron volt.
Yeah. So, the electron is in the ground state, it gets a photon and jumps up to state 3. What was the frequency of the photon? All good? Oh man.
4.82 times 10 to the 54.
Could be. Seems pretty big though, but let's test it. So it's in E1 and it jumps up to E4. No, E3 is it? E1 is minus 13.6 electron volts and E3 is minus 1.51. So how much energy did it gain by jumping? 12.09 electron volts? Where did it get this energy from?
The photon.
The photon. So the energy in the photon must equal 12.09. However, you must use joules. How do we change this into joules? Times E.
But what's 12.09?
That's the difference in the two energy levels. So, is this what you hit in, Yusuf? That sounds like it. What happened last time? Ah.
It's not supposed to be negative.
Not negative, positive. This is the answer. This is a gain as it moves up.
We did this in chemistry. First semester.
Yeah, I thought you did energy levels in chemistry. Do calculations.
No, we didn't calculate, but we did this concept.
Yeah.
Because I remember when she was teaching it.
That does not surprise me. You unhappy in class? How uncharacteristically Faisal of you. Right, continue. There's a couple of videos which I recommend.
I'll tell you why.
Go on, make it good, make it
was-
juicy.
She was like, the energy is released when the electron goes up, which is totally wrong.
The energy
Is
is
released when the electron goes up the level. It's the other way around. When the electron falls down, that's when it releases the energy. Right or wrong?
when the electron falls down, it
Ele-
releases energy in the form of a photon.
Yes.
Correct.
What she was saying
Yeah.
was, it will release the electron will release the energy when it goes up the level.
Oh,
That's why I was like, no, this is wrong.
you said it just like that?
No, obviously. I fear for my life.
Good. It's okay.
Do I have a point in being upset about the way she was teaching it?
I don't have any point in being upset.
You understand where I'm coming from.
No comment. Right. Now, there's a couple of videos here for you to watch, but I'll tell you something pretty crazy if you think about it. The videos was going to explain something which I'm trying to demonstrate.
Do you need a volunteer?
No, I don't. I do not, but thank you anyways. Now, you remembered...
Should I stand on it?
No, what? Yeah, here we go. Here is two slits in the gap there, okay? If a wave comes into both of these slits, the same wave enters both these slits, and when it comes out from this side, you learn in waves you have constructive and destructive interference. So some of the waves add together and some of the waves cancel. And yeah, you'll get this pattern on the wall. There'll be places where the wave is highest and places where it's lowest. If I use light, what will I get on the wall?
Slits.
Slits, yeah. The brightest one will be here in the center. Then one on either side, not as bright. And then the next one, not as bright. And you have the formulas for this. You have n lambda equals d sine theta. And then the other formula I always forget, x equals lambda small d over big D. Yes? Or something like that.
S is equal to lambda d big D
Over small. Anyways, this is how you can tell if you have a wave or a particle. Because if I have a particle like me, if I try to enter the double slit, I cannot enter both.
We have to create a new door for you.
Well, in this case, we'll have to increase the slit width a little bit here. Just a little bit.
Just a little bit.
Fine. Right. So if this particle tries to enter the double slit, it has to choose. Does it enter the left or does it enter the right?
But the gets reflected.
Or sometimes gets reflected, correct. But if it does pass through, it can only go to the left or right. 50-50 chance. Half the time, it'll go this way. Half the time, it'll go this way. So, the particle enters, hits the wall, splat. Particle enters here, hits the wall, splat. So what picture do I have on the wall? Just two. Just two.
Okay.
One right here, and one right here. But if it was a wave, what would I have? I'd have one right here, then here, then here. So, this is how I can tell if the particle is a particle. How many slits do I get? How many fringe patterns do I get? How many dots do I get? Two. One here and one here. If it's a wave, more than two. Okay? So let's test this out. If I shine light, it will see a wave. Sound, wave. X-ray, wave. Footballs, won't work. This is not set up at all. Footballs,
Nice.
calm yourself down. Footballs,
Balls.
particles. Thank you. Yes, two balls will be here. Thank you.
Coincidence.
Sandwiches. No, particles. Particles, that's what I'm looking for. Okay. Annoying students.
Oh, I replicate quickly.
One. What will I get?
Particles.
Particles, yeah. If I have many annoying students to fire through there. Okay, last one now. Electrons. What will I get?
Electrons. Particles.
If I fire electrons too, I should get particles. So imagine you did this experiment and you got a wave.
Oh.
Because if you do this experiment with electrons, you get a wave pattern. So this tells you that electrons are actually
Nice.
no
Waves.
Waves. What? Yes.
Yeah, we determined that eventually.
No. Are electrons waves?
No.
No, because they're
Yeah,
small
but-
charged particles. I told you at the start. explosions at the start. Be quiet.
Well, they have a mass.
They have a mass, exactly. So you might be thinking, how could an electron be a wave? After all, it has a charge. It has a mass. It's a point in orbit of a proton. How could it be a wave? Think about this. If the electron enters here, it decides to go here, or here, or here. It doesn't travel as you expect the particles to. It travels like a wave. So people were thinking, okay, so what's happening here? Maybe the electrons, when they move, they interact with each other, and they cause it to behave like a wave. But it's not really a wave. Maybe the electrons are interacting in some way. So what they did was, they sent one electron in slowly. So the electron comes in, lands on the board. Then, later, after it lands, they send another electron, lands on the board. So then they wait a few hours, and the picture that they get on the board, back to a wave. So the electrons are not interactive. So they might be saying, how is the electron getting here if it has to go from here or here? I know what I'll do. I'll put a little detector right here. Oh, sorry, right here. So this little detector says if the electron goes through the left door or if the electron goes through the right door. Yes? It's difficult, I know. You might have seen it before, yeah. So the detector is placed here. The electron comes along and the detector says left, right, right, left, right, left, right. That's all it does. And what picture do we get here again?
Wait.
No! We get a particle picture.
What?
Yes. The electron, believe it or not, if the electron is detected in its motion, it will behave like a particle again. Hey, that's it. We're doing waves and particles.
Waves and particles. Is it the one where the atom changes?
Yes, it is.
Okay.
It's exactly what we're doing. See, everybody knows this. This is common knowledge. Correct. This, yes. Huh?
Yeah, Sean was telling me about that.
Oh, you kids? Yes. Naturally. Yes, the September student studied this. So, the electron knows if it's being looked at. And you might say, no, Stephen, that's stupid. Maybe the detector is like pushing the electron. No, if you could shrink down to the size of Mr. Atom electron scale and just look at which way the electron goes, the electron will behave like a particle.
That means they have like a brain or something.
What are you even saying?
No, it doesn't.
I'm saying, quite clearly, if the electron is being observed in its motion, it will behave like a particle. If the electron is not being observed in its motion, and you only see the end result, it will behave like a wave.
Okay, question.
Excellent question. I don't have an answer.
No, how do they see it like that, behaving like a wave?
Yeah, so if you put the detector here, then the pattern you get here will be dots here and dots here. Then you turn the detector off.
On.
Yeah, you turn it off, back to a wave. On,
Impossible.
This is 100% true.
What is
Maybe
this?
it's the
Quantum mechanics. This experiment is called the double slit experiment.
Detector has nothing to do with it.
No, it doesn't matter if it was a human being looking at the electron move through one of the slits.
So literally it was being observed.
Yes, exactly, that is the correct word, being observed in any form. It will behave like a particle.
maybe it's the point of view of the person. It's like an
Yes, you might think maybe something weird happened there. So, you might think, right, what I'll do is, I'll put the detector right here. The electron has to decide if it's a wave or a particle before it enters the double slits. Because if I put the detector right here, that's after it's made the decision to move through the slits like a wave or a particle. Agreed? Yes, agreed. So you put the detector here, the electron moves through, you turn the detector on, back to a particle. Turn the detector off, back to a wave.
That detector
Even
is
if you
doing
put it
something.
there.
Even if you put the detector right here, right before
The
impact.
detector is doing something.
No. So how did they observe it being a wave?
You look at the electron just before it hits the board. If you're observing it in motion before it hits the board, it'll behave like a particle. Even though it happened to decide earlier in its journey, it's as if the electron can decide later if it wants to be a particle or a wave at the point passing through the slits.
Something
Look,
wrong
look,
with
look.
that.
Right now I'm an electron. You are the detector.
Yeah, so if I don't
I
look
want
at you...
No, look. I want to be aware. I don't know you're there.
Yeah.
So I'm aware.
Yeah.
So I'm coming here. Then I see you. Then I come back and be a passer.
Yes.
No!
But then that's saying that the electron has a wave.
Yeah, they have.
Like conscious, subconscious.
Not necessarily. No,
How can it decide? Like how can it take a decision instead of
it's all part of this. I'll give you just one more experiment to think about, and you can tell me what will happen. So you might think, okay, this time what I'll do, I'll have the detector here, like normal. I'll send the electron through, but this time, rather than look at the board, I'll just record the picture and save it on the computer. I won't look at it. I'll just record it. And here, the detector, I'll record the file as well. The file will be like left, right, like a document. Do you understand what I'm saying? So you have two saves: the detector save and the JPEG of the board. If you get it, okay. So you open up the JPEG and you're like, oh, it's a wave. Of course, or it's a particle because the detector was on. You turn the detector off and you look up the picture and what will you get? Sorry, I put that backwards. If you turn the detector off, the picture will be wave. You turn it on, it'll be particle. Now this is the crazy one. You turn it on, the image should be particle. You delete the file.
No.
You delete the file of the detector, and the image will be a wave.
No.
Well, I don't understand this.
Again.
You turn the detector on.
Yes.
You save the results. You don't look at the results. You save the results.
Yes.
You save the result here.
Yes.
Before you open the picture, you expect to see a particle here because the detector was on.
Yes.
Before you look at the picture, you delete the save of the detector and you open it up and you get back to a wave.
No. Okay, what if you
Open
take the
the
file
window.
from
Open the
other
window.
place? Like, that does not make sense. Either our minds not comprehending something or...
You want them to watch a video that...
Well, I put the links on the, yeah.
Okay, go back down to see take a picture of it. What if you put the detector on the other side? You will get water?
You delete the file and change it.
Correct.
The picture changes.
Correct.
The picture you said, why were you...
Correct.
So is it like a wave?
The picture that was vertical will change back to wave.
Or it behaves like
The picture. Well, it's only, I mean, if you open the picture and then delete the file, it's too late. You've already seen the picture. I just mean the first time you open it. If you open it up and delete the detector file, it's like the detector was never on. Even though, of course, it was on when the picture was taken.
Yeah, I know.
Wait.
The first time you see it.
Yeah, the first time. Oh, you're thinking it's then later you delete the file, the picture changed. No. It's for the first time you open it.
Wait, I want to...
This is what the September students had to study for listening, yes. So you can look at this later, Faisal. You can look at it later. Okay? I'm giving you things to do this evening. You can look at it later. So quantum
Study this evening.
yeah, this is study. Quantum mechanics is strange, as you can very see. So the moral of this particular experiment is particles can behave like waves, and waves can behave like particles. So an electron or any small particle may behave like a wave. And not only that, there is a formula to calculate the wavelength of the electron, is given by this, h over p, where p is the momentum.
No. This is for
The wavelength of an electron when it is behaving like a wave.
when was the study made?
This was, again, about 100 years ago.
And
However, the more recent experiment with the saving of the files is maybe 4 years ago. But the original experiment was 100 years ago.
The end is near.
Yes.
Oh, it's been going for 100 years.
This, you are right to ask questions like, how does the electron know it's being observed? And the other question is, what counts as an observation? If I look at it, that counts as an observation. If a cat looks at it, does that count as an observation? What exactly is an observation anyways? These are all valid questions.
Which they don't have an answer for.
No, there are answers, just no agreed
Theories.
answer. Yeah. Okay. Now, next, and possibly, yeah. Right, so here's a quick one for you. An electron fires an electron at this speed at a screen which is 1 meter away. Part 1, what is the wavelength of the electron? That's h over mv. Calculate that, please. Right, what answer did you get for the first one? What was the first one? Right. Omar, sorry, what? 6, thank you. And what is light? Right, so what answers did you get, guys? Okay. These electrons are fired at a double slit with a separation of 10 minus 10. What is the angle of the first order diffraction? So that formula is n lambda equals d sine theta. Do you know the n? Yes. What is it? 1, first order. Do you know the wavelength? Yes, because we just worked out the frequency. Yes?
Yes.
Do we know the slit separation? Yeah, and do we know, or we want the angle then? So we get theta equals sine inverse lambda over d. And what's the formula for lambda? V over f. Yes? What's the V here? 0. Yeah, well, actually, no, it's 0.1 C, because it's an electron, not a light. Oh, sorry, did we get the lambda and not the frequency? Did we? Oh, apologies, we did, yeah, sorry. So we have the lambda, so what was it? Oh, so I can just go onto my calculator then. Sine inverse lambda over 10 power minus 10, and the answer is 14. Yeah?
14 joules?
14 degrees. It's the angle we're getting.
Oh.
And finally, the fringe separation. That's this formula, isn't it? X equals lambda, this one over this one, yes? Okay, do I still have my lambda here? I do. And I said it's 1 meter away, didn't I? Yeah, 1 meter away.
I think you're using the wrong answer.
Do you think so?
Because you have to...
I got it, I thought I got it back. Yeah.
Okay.
Lambda times 1 over 10 power minus 10. 24 centimeters. So the electrons will separate on the board by 24 centimeter separations in their wave pattern.
Where can I do this experiment?
What's the big thing?
The distance
The-
between the slits in the board.
Where can I do this experiment?
At a university.
What we do as engineers?
What
Not as engineers,
Yeah, what-
only as physicists.
what professor will I have to talk to?
Any professor that does anything with atoms, particle physics, nanotechnology, anything on this scale. It's a
They
standard.
have it in GMIT?
Oh, they'd have a physics lab. And the question you need to ask is...
They have the equipment.
No, not even that. They'd have the equipment if they teach subjects like particle physics, nanoscience, stuff like this. If they teach this, then they'd have the equipment for this. And this is like a classic experiment, the double slit experiment of quantum mechanics. There are other experiments you can do to show this behaviour. This is just one of them. And these are the questions here.
With the detector.
Huh?
With the detector.
You can turn the detector on and off and then watch the image change. What are you going to study next year?
Can.
Yeah, you won't do this.
Yeah.
Would you knock at the professor's door? Excuse me, my name is Faisal. My physics teacher taught me something which I don't believe. Can I use your equipment?
Yes, I don't mind doing it. That's good.
Is anyone studying physics next year? Actual physics?
No.
All engineering... I guess you'll just have to believe me on the internet. You should Google this topic later. There's plenty of videos on this.
I'll make my way
Huh?
to this experiment.
Well.
Video with this
Okay, who am I seeing now for Q&A? What questions do you have? Matt? And then am I seeing you?
Yeah.
For
No.
together or separate?
Both.
No. Just like the electron, you have to decide if you're a particle or a wave. So please decide, are you with it or
I'm a
without?
colorblind electron. I don't know if there's a detector or not.
I am the detector. Choose one.
I'm attending his private session, and I have my own.
Attending his private session.
Yeah, he'll be asking the question. I'll be only observing.
Will you only be observing, not interfering?
No, I will interfere when he's done.
Only if he's okay with that. Did he say